So I just want to show you a couple of things. You can see here, can everybody see from the back? Big enough? Okay. So you see I'm still using 2 iterations for inner iterations for momentum, 20 for pressure. That's my global number of iterations. I'm using a relaxation UV of 0.8, relaxation P of 0.2. Now, one thing I want to say here is that generally for a collocated mesh, it is customary to use a pretty small relaxation factor for P. Okay. Sometimes for staggered grid, you might get away with using even 0.5 for that. For a collocated mesh, usually you have to use a little bit smaller. Okay, but other than that, pretty much everything is the same. You see, this is my inertial damping factor, 0.2, which is the same as what you used for the other problem. Okay, now of course this problem is has flow separation and recirculation zones and all that, so it's a little bit more complicated, and it has inlets and outlets. Okay. So that's pretty much what it is. And then here's your mesh size, 40 by, so I'm calling this, okay, so let me see if I can draw a figure. So I think this was H. This was 10H, I believe. Is that right? Okay, so this is 8H right there. And this is 2H. This here is also H. So we are using 20 node points here. Okay, or 20 cells rather, 20 cells here, and then 100 cells, no, 200 cells in that direction. I think I said in the write-up that keep the aspect ratio 1. So if H has 20 cells, then 10H should have 200 cells. Okay. So that's the thing. Now, what I've done in my code, and I'll get back to that in a moment. Let's see here. So you will see that one of the things I've done here, let's see. Okay, so you see I've created this. Nx and Ny obviously are my total number of cells. So if I go back to this picture here, this whole thing here, I'm calling Ny, total number of cells in the Y direction. And then this 200 is my Nx. Okay. The number of cells here, this one here, I'm calling Ny underscore in. Okay, which is the same as here. Okay, and then up to here. So my numbering still starts here. This is my I equal to 1, I equal to Nx, okay? And then my J equal to 1, J equal to Ny. All right? This cell here, this row of cells here, so if I draw these here, this one, for example, we are calling I equal to Nx underscore in. Okay. Actually, this is Nx underscore in plus 1. This cell here is Nx underscore in. So Nx underscore in is 2H, whatever corresponds to 2H, that's going to be equal to 40. Okay? So there are 2 extra variables I'm using for my loops. One is called Ny in, which is 20, and the other is called Nx in, which is 40. Okay? So if I break up my loop in the inlet section, my loop will run, so you can see here, if I created a fictitious cell here, this will have index Ny underscore in, and this here, the first inlet cell will have ny underscore in plus 1. Okay, so my loop in the inlet section runs from ny plus 1 to ny, and in the x direction from 1 to nx in. Okay, everybody got that? So that's the numbering we are using, all right? And if you look here, I have these two extra variables that I've created, like I explained to you. Okay, maybe I can draw it here. No, I cannot. Okay, so those are the two extra variables that I've created, all right? Other than that, everything is the same. Length in is nothing but the height of the inlet section, the length of the inlet section, and the height in is the height of the inlet section, which is 1 centimeter, 0.1 meters. Okay. Pretty much now, of course, this code that I have also introduced the energy equation, so you see these values of specific heat capacity, universal gas constant, and so on. All right, so those things are there, but other than that, it's straightforward stuff, nothing. Now you see I also have U phase and V phase, okay? In addition to my cell center, U, V, pressure correction, temperature. Of course, I also have viscosity, conductivity, specific heat capacity, density. Okay, but I have U phase and V phase as well. Now, the way I've numbered my velocities is as follows. Draw another sketch here. So here's what I've done. For any cell, I've numbered them 1, 2, 3, and 4. Okay, so 1 is east, 2 is west, 3 is north, 4 is south. It's totally up to you how you want to number it. Okay, now code-wise, I've done it this way, but if I were to do it today and if I were to run a general purpose code, I wouldn't. See, one of the things you have to learn is when you develop code, make it easier for yourself, help yourself. Okay, so one way to do that is if you, let's say, want to remember the numbering pattern. Okay, all you do is up on top, you just define 4 variables, E, W, N, and S. Okay, and you simply say E is equal to 1, W is equal to 2, N is equal to 3, and S is equal to 4. You define them up on top. So as a result, now suppose I want to write my velocity. Okay, I can write it as I, J, E. I already know this is the U velocity of the I, Jth cell, the eastern phase. I don't have to remember what that number is because I have already defined it up on top. So it will get into the first slot of that array. Okay. Similarly, I can say U, I, J, W. When I'm coding, obviously I know that means it's the eastern phase velocity or the western phase velocity. I don't have to remember that, 1 is east, 2 is west, and so on. You see what I'm saying? So use letters instead of numbers and just define the letters as the numbers up on top. Okay? So that's just a coding tip if that's how you want to do it. Okay. Now, as I said, there are many different ways of doing this. This is just one way of doing it. Okay. So let's see now. So that's what you're seeing here. This U phase basically has a dimension or a size 2. Now, of course, you see it's 2 instead of 4, and then the reason is because I don't want to store the U velocities on the northern and southern phase. It's useless. Okay, so that's why I have created only 2 slots, and same thing for the V velocity. I've created only 2 slots, the east and the west. That's it. Okay, and for V, the north and the south. Whereas you see for density, I have 4 slots. right here, because I want the density on all four faces. Okay. That's pretty much it. There's nothing, and then these are the boundary conditions, you know, for each of the variables and so on, and then the residuals and so on. So this is the basic data structure, and then of course you have the inlet velocity, and I have a comment here which says that 0.1 corresponds to Reynolds number of 100. Okay. All right. So that's my data structure. Let's go to the main program here. So this is all standard. You can just get it from your original code. You know, you can see this is the dx, dy. You know, I've divided by the number of cells in the inlet section to figure that out. I've initialized my, okay, so this is one important thing. Has anybody gotten the code to work? No. Okay. You have? What's that? Okay, so you tested it for the driven gravity problem. Okay. Okay, so this is one thing I wanted to talk about. So see here, initialization, normally for the driven cavity problem, for example, I think most of you used zero velocity to start with, right? See here, notice that what I'm doing here is that I'm initializing my u velocity as the inlet velocity rather than zero. Okay? And there's a reason for doing it. You know, you can do it either way. Obviously, it's an initial guess. But it so happens that if you use zero, then you encounter a problem. Okay, and I'll explain that in a moment. And you see the u face velocity also, I've initialized it as zero, as inlet velocity everywhere. Okay, so on all eastern and western faces, it's the inlet velocity. Okay. Obviously, at the first phase, it should be the inlet velocity, but I've initialized it to the inlet velocity everywhere. Okay, now why are we doing this? Let's just talk about this briefly. Okay, I'm going to draw another picture here. So suppose I want to draw, I want to solve a flow problem, okay? And let's consider just the first cell right next to the inlet, okay? Now here you have a wall, and let's just talk about these two being walls, because the v velocity we are setting both to zero, initializing both to zero. So there is no mass flux across those faces. So let's say they're blocked off. It's really like a one-dimensional problem, right? So what are we doing here? We are bringing in u in here. And let's say you start your calculations with u equal to 0 here. Okay? Cell center here, 0. So when you upwind, okay, this becomes 0 also. Now, if you think about this, there's a big problem here. The problem being that I have a huge mass imbalance. So the very first iteration, when you solve your pressure correction equation, you're going to have a huge mass imbalance. And because of that mass imbalance, what will happen is the pressure here will, you know, because it sees that there is a huge mass influx, it'll shoot it up so that the next iteration, you know, the pressure here is very high, the pressure here is low, it drives out the flow. Okay? So right off the back, you encounter a situation where things are perturbed heavily. You're starting with a huge mass imbalance. Okay? And that will often cause divergence. So to help that, my suggestion would be you start with inlet velocity everywhere. What that means is you basically have zero mass imbalance. Okay? Now, of course, you know, I'm making this argument, but once you solve your momentum equation, things should become better. But the momentum equation, same thing happens. Think about this. Your rho u is your momentum link, advective link, right? The mass flux, basically. So here you have rho u in, Here you have 0. So if you think about momentum balance, there's a huge momentum coming in here. There's no momentum going out there. Okay? So what will that do? You know from Newton's law, change in momentum is directly proportional to the external force, right? So what this will do is it will make the flow accelerate heavily in that iteration, because there's this change in momentum that has to be balanced by something else. So in this case, basically the pressure. So whether you look at mass conservation or momentum conservation, it's really like, okay, on one phase I have a huge value, in the other phase I have no value. Okay, and that causes immediate problems. So that's why my suggestion is that you start off with the inlet velocity everywhere. Okay, just like you did for your your driven cavity problem, do the same kind of tests here. First iteration, after you have solved your momentum conservation equation, you should see values bounded between, so suppose u is equal to 1 here, u is equal to 0 here on all these walls, right? And you solve just the momentum equation to machine accuracy, you should see all your u velocities bounded between 0 and 1. There should not be any bulging or any of that. Okay? So check for that. This is again like a scalar equation, scalar advection diffusion equation problem you're solving. All right? So check that, check your V momentum equation also, and then check your pressure correction equation. All right? Once you're satisfied with all three and you're sure that you can get them down to machine accuracy, then couple everything. Okay? All right, let's move on now. So that's, I just explained what we are doing here. Now the pressure gas, again, we are keeping at 0. No change there. These, of course, again, I've set it up so that it can run compressible flow problems too. That is homework 8 of your or homework 8 that I assigned, where you make the density a function of ideal gas law. So you see what I'm doing here is I'm saying, okay, my viscosity and specific heat capacity are constant. And then if it is a compressible flow, so I have a flag up on top, which is either set to true or false. Okay. So if it is set to false, then it goes in here and says, okay, rho is equal to whatever the constant value of density has been specified. And same thing for all the boundaries. Okay. Otherwise, you calculate your density from the equation of state, which is your ideal gas law. Okay. I've already initialized my temperature, so it can then use that temperature too. Now, this is a vector operation. It seems like a scalar equation, but it's going to do an array operation. Okay. So it's going to calculate basically the density at all cells. So it's initializing the density essentially. Here are your boundary conditions. Here is what we are doing. See, we are setting U at the left face, the entire left face, to U in, and then from 1 to NY in, that is this section here. Okay, if I can go back here. So from here to here, I'm just setting it to 0. So I'm setting the whole thing to U in and then overwriting that bottom part. Okay. Now, of course, I'm going to set up my solution domain so I don't solve for this region. But be that as it may, just for safety, that's what we are doing here. All right. And the rest is all zeros. Here's the inlet velocity. And then you can see what I've done here. 2, remember, is west for me. I've set it is equal to the inlet velocity. Okay. So on that top section, the western face velocity, I've set it equal to the inlet velocity. Okay. Now this quantity, this guy here, is something we will calculate using PUIM down the road, but it is already set to that for that first western face. Okay. Notice that this is I equal to 1. and 2 stands for west. Right? Got that? Okay. So all that is done. Now we are getting into the global iteration loop. This is pretty straightforward. This is calculating links. Now you see I have this input here. Okay. We'll get to that, what that actually does. But generally speaking, you will call one link coefficient routine, and then you will solve your x and y momentum. As we know, the link coefficients are the same for both momentum equations. Okay. Then you will calculate your phase velocity, because to calculate the mass imbalance in here, you're going to need phase velocities. Okay. This is where you use your PUM, solve for your pressure correction, correct your velocities, correct your pressure, check for convergence right here. Okay. And then you're done. Back to the beginning of your loop. Okay. That's pretty much the solver. So the first thing we look at is this link coefficient routine. So here's what I'm doing. Remember, I'm coming in with this input, okay, and I called it var u. So notice what I'm doing here. I'm saying that if that input is equal to whatever the variable number for u or v is, then set gamma equal to mu, and this variable RCP, I'm saying set that equal to the density at the face. If not, which would be for the energy equation, okay, then set gamma is equal to thermal conductivity, and this RCP as density times specific heat capacity. Okay, it's the same link coefficient routine, which is calculating the links for both energy equation and momentum equation. Okay, in one case, it is setting the gamma equal to mu and the density equal to density, basically. Okay, and in the other case, it's replacing density by the density times specific heat capacity and gamma by thermal conductivity. Okay, so that's just a top level decision. Now, notice here that one of the things I'm doing here is, again, this is for compressible flow really that it comes into play. It has to calculate the phase density, because to calculate my link coefficients here, remember the CE has density at the eastern phase. Okay, so it is going to calculate this, it's calling this function called rho phase, which calculates the phase density by interpolation. Again, this is only required if you have a compressible flow. If I go into this function, you will, I'm not going into that function here, but if I went in there, you will see it simply says rho phase is equal to constant value of rho if it is incompressible. If it is compressible, then rho phase has to be calculated from the cell center values by interpolation. Okay? All right, and then you get into this calculation of the link coefficients. Now you see I've broken it up into two loops, and this is where the picture that I had drawn comes into play. So let me just go back here one final time. Okay, and I'll draw a new picture here. Okay, let's see. So I have cells here. This cell here is ny underscore in plus 1 and 1 comma that. Okay, this cell here is 1 comma ny. This cell here is nx in comma ny in plus 1. Okay, and then this cell here is nx in comma ny. Those are the indices. Okay, so if I were to run a loop, let's say for this portion here, obviously first thing is I'm going to avoid some of those corners. Okay, I'm basically going to run it just that part, this part here. Okay, then I'm going to run another loop which goes through that part, the left boundary. Then I'm going to run one which goes through the top boundary. Now the top boundary can actually include this cell because this is really not a boundary cell. There is no boundary to the right of it. It's an interface. Okay. Similarly, the bottom boundary can actually include this cell here because it's not really a boundary cell. Okay. Yes, there is a southern boundary, but so there's a southern boundary here too. It's the same thing. Okay. So you don't really need to run 9 separate cases. You have one interior, one bottom wall, one top wall, one left wall, one top corner left, one bottom corner left. Okay. For the inlet section. Then for this section here, again, you're going to have one which will cover all these interior pieces. And then you will have one for the top row of nodes, excluding the far corner here, because that is a special boundary condition. Similarly, you will have one that runs from here all the way up to here for the bottom. Okay, you will have one which runs here all the way up to there. One special corner node here, one special corner node here, one special corner node here. Okay, so you got to break up your loops such that all the regions are covered separately. That's the complexity in this problem. All right, now I just want to show you here what I'm doing. So you see the interior cell, first of all, this is the inlet section, I'm calling it. Okay, so that's that tiny section up on top. You see, I'm not going from 1 to nx in, I'm going from 2 to nx in, because 1 is the row of cells right next to the inlet. Okay, and similarly, I'm not going from ny plus 1 because that's a corner cell. Okay, I'm going plus 2 to ny minus 1. All right, so this is the interior cell. These expressions that you see here, they are identical to what you had in your notes. Okay, so there is nothing here. You see there's this gamma interpolation, and then there's this cell density at the face, U face, 1, 2, as you know, are east and west, and then here's your switching function, and then finally those expressions that you're familiar with the switching functions. Okay. Similarly, I'm doing outlet section bottom part, outlet section top part. So these are all the interior sections. Now I go to inlet boundary. This is I equal to 1, and then I'm scanning over all the J's. And this is where you will see the, the inlet velocity has already been set into the face velocity. So it's already in there. So really there is nothing except that now you have this diffusion term show up. Okay, because the inlet velocity is known right there. So that shows up there. And then vertical left wall boundary. So that's the bottom boundary, this boundary here. Okay, your geometry is like that, right? So there's a wall there. That's the vertical wall we are talking about. So you can see this is I is equal to nx in plus 1. And then j going from 2 to ny in. Okay. Then you have a bottom wall boundary, which is the standard boundary. There's one for the inlet section right there, and then there's one down below in the bigger channel. Okay, so here's the inlet section, and then here's the outlet section. Okay, inlet section has a j value of ny in plus 1. Outlet section has a j value equal to 1. Because the way it's numbered is j equal to 1 at the bottom, and then this one is ny in plus 1. Okay. Top wall is pretty straightforward. It's a long wall, nothing there, no break there. So it's going all the way from 2 to nx minus 1. I'm avoiding the 2 corners. Okay, j equal to ny. All right. And then outlet boundary, similarly, it's a long outlet boundary. There's no breakage there. This is I equal to nx and j going from 2 to ny minus 1, again avoiding the two corners. Okay. Inlet bottom. So this is now getting into corners here. Okay, so you can see I is equal to 1, so that's this corner here. And ny in plus 1, then inlet top, which is I is equal to 1, and then that top corner. Okay. And then vertical wall bottom corner, so that's that corner where you have the recirculation. Okay. Outlet bottom, which is the far corner bottom, and then outlet top, which is the far corner on the right. Okay. So those are all the link coefficients for the different regions. There are a lot of loops, unfortunately, because we are having to break up the domain into many pieces in this case. Okay, but as far as the coding is concerned, there is nothing special. You just have to be careful when you cut and paste. Okay. Fortunately, you don't have to do this again for the v momentum or the y momentum. It's the same thing. Okay, it's the same link coefficients you're using. In fact, you don't even have to do it for the energy equation. It's the same thing. That's what we're doing here. Remember, I simply, into this array, I put in density at the face when it's the momentum equation and density at the face times the specific heat capacity at the face when it's the energy equation. Okay, that's all. Any questions on that? All right, now, next thing is the solution, of course. So let's just look at one of the momentum solvers. Again, you have to break up your loops. Okay. So, row Y sweep, bottom wall, bottom row. Okay, so I'm starting from the bottom. Now, the bottom doesn't have this inlet section. Okay, so everything is starting from that index, nx in plus 1. Now, just like I had done for the driven cavity problem, I'm creating a local index which resets that guy to 1, because now I'm going to solve n equations. Okay, that n is different from the total number of cells in that direction. Okay, so that's what we are doing here. We are resetting the index, and then of course everything else is the same. Here's your diagonal, which is the diagonal that you have calculated times 1 plus alpha. Okay, inertial damping factor. Here's your C, which is your eastern coefficient. Okay, and then there is the south and north diffusion coefficients. There is the east and west pressure. Now notice here that this is an inlet. This is a wall, right? So wall means, now if you think about eastern pressure minus western pressure is equal to cell center pressure. Remember we talked about that boundary layer theory we are using, okay, for extrapolation of pressure. That's what it's doing here. Western pressure is the cell center pressure. Okay, and then inlet pressure, eastern pressure is the north plus east divided by 2. Okay, and then this is your right-hand side vector. So notice that you have the pressure source right there, and then the northern coefficient you have transferred. The southern coefficient you don't have because it's a boundary condition, and instead you get this 8/3 and so forth. Okay, so this one of them comes from the southern term, the other comes from the western term because it's a corner for this for j equal to 1. Okay, for I equal to 1, and then you're going for the rest. This is the entire bottom wall. Okay, and then finally you're going I equal to nx. This is the outlet now. Now outlet, notice that the eastern face pressure is nothing but the boundary condition that you've set. Okay, this press R is nothing but the pressure at the right wall. Okay, which is equal to 0 because you're using gauge pressure of 0. But that's what this is. This is the pressure at the right wall. It's been set to 0 somewhere else in the code. Okay, and then you call your tridiagonal solver and you update your velocity. Okay. So this is what we're doing now. Notice that there's again a resetting of index here because you have to set it in the appropriate slot. All right. Then we are doing the interior rows. So this was the first row, then you're going interior rows, j equal to 2 to ny in, okay? Same idea, and then you're doing bottom row of the top inlet section, which is this first long row, okay? Now that has to be broken up again into two sections, because part of it is a wall, part of it is just an interface, regular interior face, okay? Everybody with me, what I'm talking about here? So let me just pop up this figure again. Right there. So if I'm looking at this row, if I'm looking at this row right there, okay? When I'm setting up the tridiagonal solver for that row, I have to be really careful. First of all, the first element has to be set up specially. Then from here all the way up to here, this part has to be set up one way. Then from here all the way up to here, I have to set it up another way, because these cells here don't have a southern boundary. The link coefficients will be different, okay? And then I have this part here, okay? So just be a little bit careful when you do all this, okay? Now there are, again, many different ways to do that. You can set the southern link coefficients to 0 at the wall and use that everywhere and run one loop, or you can do it separately, whichever way you want to do it. Bottom line is you have to be aware of these things, okay? So this is what is being done here. And then we are doing top inlet section and so on. Interior rows for the top section, and then finally the top row, okay? So this is all the row-wise sweep, and then similarly for the column-wise sweep, you're starting here, you go up to here, and then the first column that you have, part of it is a wall, part of it is a regular interior cell, okay? Again, you have to be careful there. So that's pretty much it, and you know, once you go through that, I mean, I'm not going to go into the details here. That's the momentum solver. The Y momentum solver, very similar, really no change there. And then you go into your phase velocity calculation. This is a little bit special in this case. Fortunately, this is all messed up, so I have to use... Let's see if I can make this bigger. Sorry about this, my formatting is all messed up in this one. But this is basically the idea here. Okay, so I want to calculate this guy. Okay, remember this index 2 stands for the western wall. Okay. So what we are doing here is we are calculating, so I'm using notations very similar to what you have in your notes. dpdx at node north, dpdx at node east, dpdx at node west, dpdx at the eastern face, dpdx at the western face. Okay, so these are pretty simple expressions. As you can see, dpdx at north is p east minus p west divided by 2 delta x. Okay. Similarly, at the eastern face is east minus north divided by delta x. Okay, so these are just your pressure gradient expressions, and then you simply put everything into your PWM expression, okay, which is the standard expression. So that's all there is to it. The other thing that you have to worry about is boundary conditions. Okay, so in some cases, you have to, let's see here, you have to do special treatment to these pressure gradients because you don't have a cell to the east or the west. Okay, so some of these pressure gradient expressions will change, and also in some cases, you will have to set the phase velocity equal to, for example, the inlet velocity. Okay. So those are things, and you can see it here, for example. I'm setting the phase velocity equal to the left boundary velocity, which is the inlet velocity. So when you do your PWM, this is something you have to worry about, okay? And then right at the end, after I finish the u velocity, now I do the y component, okay? Similarly, now we are calculating dp dy everywhere instead of dp dx, and so on. Okay. So this part here is obviously something you haven't done for your staggered mesh and needs to be done. Okay. Once you do that, the pressure solver is similar, no change as staggered mesh. Okay, again, you're calculating your m dot. Let me see here. Here's the bottom row. Okay, you're calculating your m dot. You have your link coefficients. Okay, and then you're setting your diagonal and your off diagonals. All right, and finally calling your tridiagonal solver. Okay, and then just upgrading your pressure. All right, so this part here is the same as what you had for a staggered mesh, the structure of the solver. Okay, and once you solve your pressure, the final step is, of course, again, this is messed up. Not that, sorry, here. Sorry about that again. I'll just make a portion of it bigger. So just to give you an example, this is your velocity correction. The only difference between what we have here and what we had in the staggered mesh was, in a staggered mesh, if you look at your expression, you had a I and I minus 1. Here you have I minus 1 and I plus 1, okay, because there is no staggering. So you're really looking at two cells across, and then this half is basically nothing division by a 2. So instead of division by a naught, you have division by 2 a naught, okay? That's the only difference. And again, here you have to be a little bit careful when you get to boundaries. All right? So that's your, okay. The other thing I wanted to talk about here is that you also have to correct cell face velocities. Okay? So remember that. We have to do both cell face and cell center. Okay. All right. So after that, we are basically back to square one. After we've solved the pressure correction, corrected our velocity, the pressure correction is, this is the same as before, one line, no change. Okay. You're simply doing omega p times pressure correction. It's a global operation. All the cells get corrected in one shot. Okay. And that's it. You're back to square one. After that, you're back to the beginning of the loop. Any questions?